Effect modification is the idea that the effect of a variable on an outcome can be dependent on a third variable. The effect is modified or changed based on some other variable. Effect modification is a real world phenomenon. There's a story as to why a car that's 1 year older has a differential effect on price depending whether it's a classic car or whether it's just a normal run-of-the-mill car. Let's look at an example of this. This idea of effect modification can be thought of with this word depends. The relationship between x1 and y, in other words, the slope, right? Relationship is slope or beta. That relationship depends on x2. In other words, you're going to have different slopes. For a classic car, the older it is, positive slope, price goes up. For a regular car, the older it is, the price goes down, negative slope, different slopes. And so we're going to assess effect modification by looking at slopes. Now, effect modification, you want to find it. You want to look for it. You want to find it. These are important things that you're discovering truths about the real world. In fact, sometimes looking for that interaction actually is the research question. Let's review. Multiple linear regression. We have this data set trying to predict house selling prices. Regress, price, age, and then we had this variable northeast. Northeast was a binary variable for the location of the house. How is the house's selling price predicted by its age and its location? We get a regression model that says price, intercept, slope, location. Both of these are significant predictors. You can write separate equations for the two separate towns. Here is the full model. Price equals intercept minus age plus whether it's in the Northeast or not. Now we can simplify the model for the two separate locations. I have this variable coded where 1 means the house is in the Northeast and 0 means it's not in the Northeast. So if the house is not in the Northeast, I can plug in a 0. If I plug in a 0 here, 0 times anything is 0. So the model simplifies to price is this minus age. Now this data set is priced in hundreds of dollars. You can't actually buy a house for this price. So price is this minus 7.6 times age. That's the slope. That is the effect of age on the price of the house for houses not in the Northeast. What about for houses that are in the Northeast? Well, if they're in the Northeast, you have a 1 for that value. So for this, we get 258 times 1. 258 times 1 is 258. And when we simplify this model, that 258 is going to go into this intercept, and the model simplifies to price equals this minus 7.6 times age. Now take a look at those two slopes. What are they? They're the same. I'll ask you a really interesting question. Why is this true? Why are the slopes the same? Pause it and think about that for a second. They're the same because you told Stata to fit a model where the slopes are the same. This is the model that you fit. You said regress, price, age, Northeast. But what if this model is inappropriate for the data? This is so important. Do not mistake the map for the territory. You have to look at the data. Perhaps the effect of the age on the price of the house depends on where the house is. Well, let's take a look. Some houses live in this neighborhood with these little red squares, not the Northeast. If you had to draw a line through those red squares, what would the slope of that line be? I don't know, something like that. It would be something positive. The older homes are worth more. And what about those green ones? I think I have a green, I have a green pen on here. What about the green ones? Well, if you had to draw a line through that, now this is really, really interesting, is that we just fit a model and the slope of both Northeast and not Northeast was negative 7.6. But what's the reality? That model is not the reality. We need to fit a model that tells Stata, hey, if you need to, go ahead and fit different slopes for the two things. Go ahead and fit slopes that aren't exactly the same, that aren't parallel. And the way we do that is we make what's called an interaction term. The interaction term tells Stata, hey, don't just draw a line, draw two separate lines, one for one group and one for the other. You make this decision, and you'll get a model that looks something like this. Now, how you do it is you have to actually make an interaction term. This is kind of weird. I remember the first time I learned this, I was like, that works? Yeah, this works. I'll show you, and I'll show you why. So take the one X variable you're interested in, take the other next X variable you're interested in, and multiply them together. This is now a new variable. It's called the interaction term. And you take that variable, it's going to be a new column in your data set, and you put it in the model. You also include X1 and X2 in the model. And now we're going to see that we're going to get a p-value. And that p-value is going to tell us, are the slopes different from each other? The null hypothesis is that the slopes are parallel. And this is going to allow the model to maybe go like this and see if they cross. Here's how you make the interaction term. You make a new variable. In Stata, you would say generate. I'm going to call it inter. So generate interaction is age times northeast. So here is my new variable. And you can see some houses are in the northeast. In that case, they get multiplied by their age because northeast equals 1. Some houses are not in the northeast. In that case, they get multiplied by not their age, so that's 0. So interaction, this variable is just a number. That is northeast times age. Then you put this number in the model. So you say regress, price. Here are those two parent terms, or the main effects as they're called, and then the interaction term. And then what you get is a new coefficient for the interaction term. In this case, it's negative 23. And what's interesting is that it's statistically significant. This tells you that the effect of age on price depends on where the house is. You look at the statistical significance of the interaction term. Now I'm going to show you why this works. Remember that when we do a regression model like this, what is the null hypothesis for each coefficient? Well, the null hypothesis is that that coefficient, or that beta, is equal to 0. In other words, the interaction term is equal to 0. And let's see how that plays out. When you write out the full model, it would be something like this. Price equals 946 plus 0.75 times age plus 574 times northeast. This is a negative sign in there. Minus 23 times inter. And remember that the interaction thing, we just made it, right? The interaction is northeast times age. So that is our model, okay? That's the model. Now we can simplify it. Remember, northeast is 0 if a house is not in the northeast. So if the house is not in the northeast, this is 0 times anything that falls out. This 0 times anything that falls out. And the model simplifies to this. Now, what if the house is in the northeast? If the house is in the northeast, we still get 946. We still have 7.5 plus age. And now here we see if it is in the northeast, that becomes 575 times 1. So that's down at the bottom here. And if it is in the northeast, this becomes negative 23 times age times 1. So in other words, negative 23 times age. Now, this is what's really interesting. If we simplify that model, the 575 goes with the rest of the intercept, and we have a new intercept. And the negative 23 times age goes with this 7.5 times age, and we get a negative age. So we see that one slope is positive and one slope is negative. How much different are the slopes? How much different are the slopes? Well, they're 23 different. They're 23 different. If the slopes were the same, how much different would they be? They'd be 0 different. If they were 0 different, what would the p-value for the interaction term be? Well, it would be not significant, because the null hypothesis is that interaction term equal to 0. So that number there tells you how different the two slopes are. And if that number's big, look, it's always going to move around a little bit by chance alone. But if that number's big, it tells you, hey, there's 2 different slopes here. There's 2 different relationships that are going on. So that statistically significant interaction term tells you these lines are not parallel to each other. They're not parallel to each other. Can Stata make those interaction terms for you? You have to go through the whole process. They will make it for you. And the way that works is regress price, that's our outcome. And then you use this double, in the year 2020, we're calling these hashtags. When I was a kid, they used to be called pound signs. When my dad was a kid, they used to be called octothorpes. Who knows what they're called when you're watching this video? But if you put 2 of them in there, Stata will, I almost said Satan, Stata will make the interaction terms for you. Now we have to put that C in because that's a continuous variable age. But you see from the model here that there's our interaction term. It's important to say this point of you don't interpret the main effects when there is an interaction. This is a very stupid statistical joke, but there was a guy who had one hand in a pot of boiling water and one hand in a pot of ice cold water. And someone said, how you doing? He's like, on the average, I feel fine. Now, that's dumb, but it's technically true. On the average, I feel fine. But if you had to call each hand and say, hey, what should I do? What should I do to recover from that experiment? You would say, well, it depends. Are you talking about the left hand or the right hand? It depends. So effect modification is all about it depends. And in epi, you learn a lot about it is an external validity issue, not an issue of internal validity. And the confusion between confounding and effect modification also arises because we don't appreciate that this is talking about it depends in the real world on something that's going on that makes these relationships different from each other. You'll see lots of examples of effect modification in the literature, and you'll get the opportunity to explore a lot of these when you have your own data to play with.